So the first question is just what are the values of those first 5 terms in this sequence? So since we have a formula, we can just use the formula. So I will stick 1, 2, 3, 4, and 5 in for n and get a sub 1 is equal to 1 over 1 squared. So on our graph here, there's a sub 1. A sub 2 is 1 over 2 squared, so that's 1/4. And on our diagram, there it is, 0.25. Like a sub 3 would be 1/9. A sub 4 would be 1/16. A sub 5 would be 1 over 25. So there are the first 5 terms of this sequence. So tell me something about this sequence. Does this sequence converge or does the sequence diverge? How come? Right, the sequence, thank you. The sequence converges to 0 because, well again, take the limit of the sequence as n goes to infinity, the limit of 1 over n squared. That limit is, quote unquote, 1 over infinity, again, and that's 0. So the sequence converges. I'm going to kind of put a little infinity symbol here and a little arrow. And we can be pretty confident that the sequence converges to 0. Just using ordinary calculus on the function f of x equals 1 over x squared. Right? That's equivalent to connecting these dots with a continuous function. And then just asking what is the end behavior of that continuous function. End behavior is another great calculus concept. And it sure looks like as n goes out toward infinity, the sequence is tending towards 0. One of the hard parts about infinity is that we can't really see it on an axis. So here's a nifty little trick that I like to do. And this one you can take to the bank. I haven't seen anyone else do this in a calculus class. Not that I invented this or anything, but I think this is a useful way of interpreting what's going on here. One of the ways to visualize what's happening way out at infinity is to take the whole x-axis, which runs from 0 out to infinity on this horizon, and we basically just want to trade places. We want to invert the x-axis and take everything which lies to the right of the line, starting at 1, and flip it so that it lies to the left instead, lies in between 0 and 1. So I'm just going to turn the whole x-axis inside out, so that where we used to have 0, now we're going to have infinity. And where we used to have infinity, now we're going to have 0. So instead of looking at our limit as n tends to infinity by looking off to some horizon at the right, I'm going to look as we go toward the left, towards 0, to find what it looks like. So just visually, here's the picture of what happens. Let's add in some additional terms. 1 over n squared, up to 50 terms here. Well, it certainly obviously looks like this is tending towards 0. But if I flip the x-axis, so notice when I flip the x-axis, 1 is now here on the right, and we increase n towards infinity as we move toward the left. So 1, 2, 3, 4, 5. So I flipped the whole x-axis so that now this point here at 0 is n equals infinity. So we brought the horizon toward us. And now when we read this limit, we're reading this limit going toward the left instead of going toward the right. And sure enough, as n tends to infinity, a sub n does tend to 0. So that's a neat little trick, and we might come back and use this trick more than once when we start talking about series. Because as it turns out, the answer to the question of whether a series converges depends on not just what the limit of the sequence is, so the sequence has to be convergent, it turns out, but whether the series converges depends not just on the value of the limit, but also on how quickly the sequence is reaching that limit. This sequence of numbers is tending to 0, but it turns out that it's tending to 0 pretty quickly. Right? As we move toward the left here, our numbers get pretty small pretty fast. And it's coming into its limit. It almost kind of looks like, what shape does this look like here if I connect these dots? looks kind of like a parabola. All right, it's coming in for a nice smooth landing at 0. Right, if I'm on an airplane, and I am not going to be very good at drawing airplanes. There we go. Yeah, no, well, not really, right? Because by the time we get to 0, we have leveled off into a nice horizontal tangent by the time we land. So this looks like a smooth landing in towards 0. But contrast that with what I have with 1 over n. So let's go back to the 1 over n example. So we'll dial the exponent here down to 1. So here's a sequence that looks awfully similar to the one we were just looking at, 1 over n squared, except this is 1 over n now. If I flip the x-axis so that now infinity becomes 0 and 0 becomes infinity, here's what it looks like. Would you like to be on this plane? No. Yeah, let me draw in my scuzzy plane again. But sure enough, I certainly wouldn't want to be on this one. Crash. So we're going to have some work to do to make this rigorous and precise calculus. But for me, these pictures underline a very important truth, that I would rather be on a plane that's landing like this than on a plane which is landing like this. That's not so good. And so it turns out that even though the limit of these sequences is still the same, because my terms are all tending toward 0 in both cases, our planes all eventually end up on the ground. Right? It's the manner in which they do so that's going to determine the convergence of their infinite series. And because this plane is crash landing, the infinite series summation of 1 over the square root of n, which is this one, is going to turn out to diverge. Whereas the sum of 1 over n squared, the one we were looking at a moment ago, converges. Returning to our table here, let's see if we can come up with some evidence, having convinced ourselves that this series, that our plane's making a nice smooth landing, and so we think that the series is going to converge, question mark. What kind of numerical evidence could we come up with to help to support that assertion? So the question of whether a series converges is answered by whether or not a certain sequence converges. And the sequence that's relevant is not the sequence of the original terms, but rather the sequence of what are called the partial sums. Now, what's a partial sum? What does the word partial mean here? Yeah, we're not going to be adding all infinitely many, because we don't know how to do that. But in a partial sum, we can add the first finitely many terms of the sequence and get a number. So the first partial sum, s sub 1, we obtain by adding the first term and nothing else. So the first partial sum is just equal to the first term. It's 1. What about the second partial sum? Right, we're going to add the first 2 terms of this sequence together, and I'll get 5/4, which we should probably get a decimal for. I'm not a huge believer in decimals, but it certainly it's going to make this question a little easier to answer. So 1.25 is our partial sum S2. The third partial sum, 1 plus a quarter plus a ninth, that's going to be 1.361. 3611. Repeating. So there's value of the third partial sum. The fourth partial sum, I'll need to add 1/16 to that. Let's see how long I can do this without a calculator. This is going to be 1.4236 1 dot dot.
Yep.
Cool. And then after that, I got one more. I got one more for you. Add 1/25 to that, and I get 1.46361, etc. Cool. I'm not going to ask you to add those in your head. You got calculators for it. I got a PhD. Whatever. I'm just showing off at this point. Okay. So anyway, those are the first 5 partial sums of the series summation 1 over n squared, n beginning at 1 and going to infinity. Do you notice anything about those partial sums that can help us to answer the question of whether the series converges? What are those partial sums doing? First of all, they're increasing. That should be happening, because why? Why are these partial sums definitely increasing? Why is that not surprising?
Adding all positive terms.
Exactly. All the terms of the sequence that we're adding together are positive. So every time I add one more term, I'm just adding one more positive number into the previous partial sum to get a bigger partial sum. So those terms are increasing. What else does it seem like they're doing? If there's any justice in this problem, if we're going to claim that this series converges, then what do we need to see happen?
It needs to approach something but not get to it.
Exactly. It needs to approach something, right? These partial sums have to level off at some value. And so if they do, if there is a finite limit here, question mark, then we will have demonstrated that this is a convergent series. So a series converges if and only if, and this is the definition, its sequence of partial sums has a finite limit. So the limit exists and is finite. That's what we mean by an infinite series converging. So these are going to be the entries in our table on that right-hand column. Right? The first partial sum was equal to 1. Second partial sum, there was at 1.25. The third partial sum, 1.361, 1.424, 1.464. Okay, those were the first 5 that we already had in our table. Let's hit the fast forward button here and see what happens. Oh, I kind of wish it stopped at the end here. Oh. It sort of, dilly-dallies around a little bit, but eventually it seems like it settles down to 1.64 or so. Let's do it with a little more precision. So we're looking at 3 decimal places here. Let's get nuts. Let's do 40 decimal places. And we'll see if we get any different result here. So hit the play button. We can go, we could go more than 200 terms, you mean? Because it does look like this one has taken a little bit of time. So the plane is still coming in for what looks like a smooth landing, but it might not be the smoothest landing you've ever experienced. Let's crank it up so we can go further than 200 terms. So let's go out to 2,000 terms instead. By the time we get out to 2,000 terms, it looks like we've locked maybe one more digit in our expansion, 1.6444. If we want to go further, we can go further. 200,000 terms, maybe? I think it's having a little more computational trouble keeping up with things. But okay, so this is the partial sum for 80,372 terms. And if I advance it just a little further, might take it a little bit to deal with this. There we go. Now it looks like my first 5 decimal places or so seem to be the same, 1.6449, etc. Add a few more terms. See, when it takes a computer this long to compute this, it's an indication that we probably need some calculus power to actually make this conclusion as accurate as it can be. But it does certainly look like the hypothesis that these numbers are leveling out seems to be suggested, seems to be confirmed by the evidence that we have here. That's not a proof, of course, but it's at least some indication that probably the partial sums, the sequence of partial sums of this series, looks like it converges, levels off to a value. It looks like it's about 1.645, approximately. But at the very least, we can feel pretty justified in thinking that this is a convergent series, because its sequence of partial sums levels off to a value, a finite value, in this case 1.6445. So there's two questions we can ask about a series, and one of them is the one that we're going to get a lot of practice answering. The other one is one that is in general very hard. The first question is whether the series converges. Does this series converge? That's going to be the one that we answer more often than not. And for this series, it looks like the answer is yes. But the backup question to that is the one we're not going to always be able to answer. But the backup question is, if the series converges, what does it converge to? And that's a hard question. Because we can come up with an approximation, 1.6445, but finding an exact value, I don't know. Sometimes we can do it, sometimes we can't. And it might surprise you to know that for this particular series, that exact value is pi squared over 6. What? Where's the pi? I mean, pi is this geometric, trigonometric thing. We don't have that. We just have the sum of the reciprocals of the squares, 1 plus a quarter plus a ninth plus a 16th. Pi squared over 6? This is a true statement, but it's not at all obvious why it should be a true statement. So the question, what does the series converge to? That one we're going to ask and answer less often. And we're typically only going to ask and answer it kind of at the end of today and probably going into Monday. And then again, a week later. Because ultimately the goal of studying sequences and series is that infinite series give us a way of taking a real number, like pi squared over 6, and breaking it apart into a bunch of really simple pieces. Pi squared over 6 is a hard number. It's a transcendental, not algebraic, real number. But if it's true that this series converges to pi squared over 6, then pi squared over 6 can be thought of as the sum of some very simple numbers. 1, a quarter, a ninth, a 16th, a 25th. So we've broken apart this really challenging object, mathematically, into a series made up of a bunch of really simple little objects. And in order to recover the whole from its parts, we have to add up all infinitely many of those parts. But that's kind of why this is calculus. We're breaking something difficult into an infinite sum of things that are easy. And this week we're going to do it with numbers, and the final week of the course we're going to do it with functions. To break apart a hard function like the sine of x into a sum of a bunch of easy pieces like x squareds and x to the fourths and x to the fifths and so on. That's the theme. That's where we're ultimately driving with all this. But before we can do it with functions, we've got to do it with numbers. And that's what next week is all about.